Okay guys, so basically with radioactive decay what's occurring is that the nucleus is either too big or it has too many protons, too many neutrons, so it starts literally throwing stuff off, or in the case of electron capture, just kind of capturing electrons that are nearby, which is actually pretty dangerous stuff. So what you need to know, if we look at thorium-232 here, we've got an alpha decay, alright, and in that alpha decay right here, our big indicator that we have an alpha decay occurring is right here. This helium atom actually gets kicked off, and we also symbolize that as our document kind of shows us here. Sometimes it's written, whoops, well, that's my highlighter, with a alpha symbol. Alright, so sometimes you'll see it like that, sometimes you'll actually just see it with the helium, that helium nucleus coming out of there. So what do you need to know? Well, you need to know what we're going to be left with when that helium actually comes out of the nucleus. So really we want to think about this almost like a just a simple math equation where the arrow is the equal sign, because whatever we put into the equation has to come out. So really it's as simple as if I look at 232, so 232 is the mass number, remember. Something plus 4 has to equal 232. Well, I know simple math here. 232, that's got to be 228. 228, there we go. And I do the same thing with the atomic number. So my atomic number down here, 90, something plus 2 has to equal 90. Well, I know that that has to be 88. Right. And I look up at my periodic table, and I find that, remember that atoms are elements are defined by how many protons they have. So that 88 really defines what that element is. So 88 ends up being, I believe it's radium. Okay, and really that's how we do all these decay problems. It ends up being somewhat of a math problem. So let's look at a beta decay, because beta decay is the one that most students actually end up screwing up. So beta decay, what's occurring is we're actually getting, and here's our the important one, beta particle. So we get a beta particle actually coming out of this, a 0 minus 1e. And same process, I just look at something plus 0 is going to equal 228. Again, think about this arrow almost like an equal sign. Right side has to equal the left side. So that's going to be 228. And then here's the tricky part that a lot of students mess up, because what they'll do is they'll put 87 here, which is incorrect, because if we remember math, anything plus a negative is going to be almost the same, or it's exactly the same as subtracting. So what I'm saying here is 87 minus 1 gives me, not 86, I need 88. So we have to be careful with beta decays, because this shouldn't be 87. What should it be? Well, 89 minus 1 plus a negative 1 gives me 88. Okay, so those numbers are going to match up. All right, and I can always go back and check my work, make sure that those numbers do in fact kind of line up. So look on the periodic table. I believe 89 is actinium, AC. Okay, so for the last two, what we have is we have a positron coming out. So a positron is really the same thing as a electron, but it's actually just exactly the opposite. It's really just a positive charge coming out of the nucleus. So when that positron emits, once it comes out, our atomic number is going to go down by 1. All right, and if we look on the periodic table, we know that 18 is actually going to be argon. AR. And that's it. So 40 plus 0, still adds up to 40. So we actually get the same thing when we do our last one here, an electron capture. So this was a positron emission. This one's an electron capture, and it might look familiar. That particle should look familiar. That's an electron. But notice, and this is the part that that defines it from a beta decay, is that electron is on the left side of the arrow. It's on the left side of the arrow versus up with our beta decay, right? That electron is on the right side of the arrow. So same process as a positron, or same result, I should say, different process. If I take 40, here's my 40, plus 0, I'm going to end up with 40, and then I also get this particle over here. This particle is beta, gamma ray. That's a gamma ray. And a gamma ray is really just radiation, and it's actually really high energy, dangerous radiation. So electron capture, really dangerous kind of radiation coming out of that. So last thing we're going to check here, we've got 19 plus a -1. Same thing as minus. 19 minus 1 gives us that 18. And then again, our radiation has no mass. It has no protons. It's literally just energy coming out of there. We look that up, and it gives us the same result of argon.